Let's do another Hardy-Weinberg problem. Yes, before we do that, well, it's like I have my own bump music. Okay, hang on one second. Dreams of Cobalt by Zircon. That's my Pandora station. Alright. I think I'm ready to go. I'm trying a slightly different format here because I'm noticing on these videos that I get this weird thing where, in fact, I can even see it now so my cursor on the streaming software is not lined up with where it is, but anyway, we shall persevere. So let's do another one of these Hardy-Weinberg problems. If this is the first video that you are watching pertaining to this stuff, stop right now. That's terrible. Go back and watch the video where I work the problem on the little force neutral bubble creatures, because I show you the formula sheet and stuff that those problems rely on. For this one, I'm going to assume that you kind of know where to find that formula sheet and we'll be okay. And let's just get right to converting the story part of the problem into the mechanics of solving for genotypic, allelic, and phenotypic frequencies, and applying what we know about the Hardy-Weinberg equilibrium to do stuff like calculate the frequencies of carriers in a population. All right, so apparently we're going to dominate the world of Galarian, which is one of my go-to fictional contexts for genetics problems, and we're back to studying owlbears. We have winged owlbears, which everybody knows are very rare. It's conferred by a recessive A allele, A standing for airborne. The dominant allele confers a sturdier but wingless phenotype. Right? So, winged owlbears are rare in nature because they have lower blah 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 details that don't matter. Right? We're going to study a nearby population of 1,000 owlbears, and we've got 12 of them that have the winged phenotype. Calculate the frequency of winged owlbears in this population. This question is so ridiculously easy that many students outthink themselves. What I'm trying to do is make sure you understand that frequency is not the same thing as a percentage. So the frequency of winged owlbears, which we know because that is a recessive allele, is equal to 12 over 1,000, which is equal to 0.012. And we know that the frequency, by the way, of this genotype, if we can assume Hardy-Weinberg equilibrium, is Q squared. This is sufficient for 2 points. Done. We need to use this information to calculate the rest of this problem. So in part B, calculate the allele frequencies of big A and little a. So in order to do that, we have to calculate both P and Q. So the frequency of this genotype is equal to Q squared. So Q squared is equal to 0.012, which means Q is equal to the square root of 0.012, which is equal to, I just realized also in the last video that when I authoritatively drop the calculator, this microphone picks up everything, so sorry for your eardrum rupture. Let us calculate the square root of 0.012 with our calculator that we will bring to the exam. I think that this joke might be getting old, and yet some of you will forget. Square root 0.012. I cannot do this in my head. 1.095. Let's round it up. 0.11. That's sufficient. 2 to 3 significant digits, plenty. I saw people writing like 8 significant digits on the previous exam. You don't need to do that. So there's the frequency of the little a allele. The frequency of the big A allele is equal to P, which is equal to 1 minus Q, and you would know that if you saw the other video where I showed you on the formula sheet that there's a formula that tells you that P plus Q equals 1. That is equal to 1 minus 0.11, which is equal to 0.89. I don't think I need a calculator for that, and if I'm wrong, I will just delete this video and all evidence of it will be gone from the internet. So, we have calculated the allele frequencies. These are the numbers that you need to actually get full credit for this problem. This part is done. Now, let's apply that knowledge to actually calculate something useful, in this case the frequency of carriers in the population. This turns out to be useful when you're doing human genetics and you're tracking things like rare genetic diseases or new genetic traits or something like that. So, frequency of carriers of this allele in the population, what we're really looking for is the frequency of heterozygotes in the population. And we know from the formula sheet from the previous video that the genotypic frequencies in a population that is in Hardy-Weinberg equilibrium can be calculated with this. This is the genotypic frequency of these individuals, this is the genotypic frequency of the heterozygotes, and this is the genotypic frequency of the homozygous recessives. So, the frequency of heterozygotes is 2pq, which is 2 times 0.11 times 0.89. Okay. Ooh, wait, this is why we're in Photoshop. Quick, before anyone notices, we have to redirect that arrow because we calculated Q first. So there's, you guys, anyway. So this is Q and this is P. I reversed it, sorry about that. I'm sad. Anyway, hopefully that doesn't throw you. 2pq, we've got Q and P up here. So that is equal to, and once again, I'm going to use a calculator for this. This is not one where I can make the math super easy, do in your head kind of math. Times 0.89 equals 0.1958. Let's just round it up to 0.196. 0.196. And just to be thorough, okay? So, again, the math in these problems is trivial. It's super easy. It's middle school, if not elementary school algebra. Mapping the concepts onto the math is the part that you need to practice, and that's why we posted these problems, and there's lots of problems in your textbook that you can practice on this as well. Okay, so that's the frequency of carriers in the population. And now I am going to bring this up a little bit, and we'll look at one of the ways that I assess whether you know what we have to assume in order for these calculations to be approximately correct. I don't know what a technomancer is, but it seems cool. This is actually a rune lord from, I digress. Some dude sequences the genome of an owlbear population and informs this other dude, Seebeloth, that the actual frequency of heterozygotes in the population is 0.35. Karzug uses a chi-square test to show that this frequency is significantly different from Seebeloth's estimate in part C. Give 3 reasons why this deviation might have occurred. So most of this is a throwback to the old part of Mendelian and transmission genetics and the idea of testing expected versus observed data using a chi-square test. But it's kind of a red herring in terms of how to actually solve the problem. What I'm saying to you is our observed proportion of carriers is, well actually this is the observed proportion, is different from our predicted or expected. So this would be expected and this would be observed in this case. They are different. Why? Probably because we violated one or more of the assumptions of the Hardy-Weinberg theory. So when I say give 3 reasons why this deviation might have occurred, you have actually 5 choices. Let's write them all out. Maybe there is migration into the population. Maybe there are new mutations. That's kind of unlikely because new mutations arise at a very low rate. There might be selection occurring in the population. There may be a finite population size, which leads to genetic drift. That is certainly the case. And then there's one, so you could pick any of these, any 3 of these to get 6 points. And there may be non-random mating. Okay? Remember, for these 5 things, we assume the opposite is happening if Hardy-Weinberg equilibrium applies. If I'm asking you for reasons why we haven't achieved Hardy-Weinberg equilibrium, then these would be the violations of those assumptions. So it's a little bit of a twist, but really what I'm asking is, does the student know what we have to assume for Hardy-Weinberg equilibrium to occur? And can they convert that knowledge into reasons why we might not have observed what we expected? So don't overthink it. It's not as complicated as it appears to be. All right, so that's the owl-bear population genetics question answered. As always, if you've got specific questions or other videos you want me to do, you just have to ask and I will do them. I'm hoping this helps, and I'll see everybody in the test. Have fun studying. Okay, we should turn the music back on for the extra, right? I don't know if this will work. I don't know. Is it working? And we'll fade to black. Bye.